Okay, so I don't do this very often, but I wanted to create a tutorial for some work I've been doing on a topic that is often fairly confusing, which people tend to get wrong or misapply or have never seen a full elaboration on. There's one new result toward the end here that I also wanted to sneak in. It is something, as far as I know, isn't in the literature, but is rather satisfying. I'm kind of a perfectionist, so hopefully I can get through this without um, without letting that get in the way. So, what exactly is this tutorial? This tutorial is a sort of full-blown introduction to calculating the critical t-value for students' t-distribution. And I've broke it up into 5 parts. I'm going to try and make each part a video in a 5-part series. I only have so much recording space, and in that sense I'm limited to breaking it up this way. I've tried to do this a few times to no avail, and the only way in which I'm going to be able to upload this tutorial is by segmenting it in this fashion. So just to start off, a brief overview of what I'm going to do. So the first thing I want to do is I want to give a motivation for making these calculations, understanding how these calculations arise, understanding how and where this sort of statistics crops up, and explain a bit the motivations behind why this method of calculating the critical t-value is so important. And then the second video, I'm actually going to derive students' t-distribution. This is something you could skip if you wanted. It's widely done in statistics classes. There are a lot of online tutorials for this, but I figure for completion, this is a step I'd like to actually implement. I'd actually like to elaborate on, just for the sake of completion. Then in the third video, I'm going to derive the cumulative distribution function for students' t distribution, and I'm going to explain how that's connected to this special function called the regularized incomplete beta function. That's I sub z of a and b. That is something which I had a hard time finding online. I had a hard time finding this, but I'm going to do the full derivation of that because it becomes important, integral to the fourth video, which will be the full calculation from first principles, an analytical formula for the critical t-value, t sub eta of v, and that is where I'll present a sort of new result which has some interesting and satisfying properties. It's a very satisfying sort of conclusion to this. And the very last thing I'm going to do is I'm going to connect back my formula, or this formula, to various numerical sequences which exist in the literature, exist on the online encyclopedia for integer sequences, etc. So that's a breakdown of everything, and I'm just going to kind of get started. So to start off, I want to look at some motivation, some motivating reasons why we should be interested. So, what is students' t distribution? Where does it crop up? basically, students' t distribution crops up in areas where we're generalizing from experience. We have some data set which represents our experience, and we're trying to generalize or bound how confident we can be in our generalizations, given we assume the reality sort of exists out there, true values exist from our experience. Also, other motivations might include, artificial intelligence or image processing or problems to do with financial risk management, evaluating statistics in public health. Or even in physics. Students' t distribution crops up all over the place, but essentially it comes from these problems where we have some limited data set, which is our experience, and we're trying to infer from that experience the generalized picture. In other words, we're trying to infer global statistics from local statistics. An example might be a political poll where, given the impracticality of polling every person in the United States or in some country, Britain, France, etc., what one has to do is randomly subsample the population and then bound how confident you can be that random subsample is indicative of the true picture, the true value for the overall population. So schematically, this sort of looks like this. We assume there's some true underlying distribution or population with a probability distribution, and some statistical measure on that distribution. For example, the population mean, which I'll indicate here as mu. And we take some random subset of that population, which is manageable, some large but manageable subset of that population. In fact, what's interesting is you can quantify how large a subsample one needs to take in order to attain a certain confidence in the similitude between the sample mean and the population mean. But basically, we have some true population and some true population mean, represented here in blue by mu, and then we have some subsample from which we can calculate a sample mean. Say we have n different observations that we make of the population at random intervals or as random as we can, and we want to know, our question is how confident can we be that our subsample mu sub n is a good approximation to the true population mean mu. And so we're going to derive some statistics which solves this problem, and this problem is related to these other things. For example, maybe we're fitting a line to some data and we want to put confidence bounds on the linear regression of the data. That is, epistemologically, that is in form directly connected to this t statistic. So this is sort of our motivation. And the way we're going to do this is we're going to look at a pared down problem, but we're going to look at that pared down problem in completion. We're going to look at it from the 0th step to the final step, so to speak. Now, in this problem, where we're comparing the sample mean versus the population mean, we have this formula. And this formula is going to help us determine or answer our question. So we have a formula here. I'll just write it out. This formula is this. It's called the upper confidence limit. And it is equal to the sample mean plus the t statistic, or excuse me, the critical t value multiplied by the sample variance divided by the square root of n, where n represents the number of samples or the cardinality of the set of observations. And I'll just write out some definitions real quick, just for completion. X bar sub n is the sample mean. So suppose we have n samples. This is simply, you know, the average of those samples. Average of those samples. And then we also have S sub n, which is the unbiased estimate of the variance from our sample. And it has a definition, a formula. That formula is the sum of the squared deviates from their mean over n minus 1. The reason why it's n minus 1 is because that's the sample variance and not the true variance. But that's its definition. So just to give a bit more motivation, or to elaborate more, this UCL term, abbreviated UCL, the upper confidence limit, this is the greatest average value that will occur for a given confidence interval. I'm going to abbreviate that as CI, and a given population size. In other words, supposing I take some sample mean, I want to know how confident I can be that that sample mean represents the true population mean. The upper confidence limit will give you an upper bound on that mean value. So for example, this may come up in value at risk, looking at financial risk management. How much can you expect to lose, sort of given the volatility of some underlying stock or something to that effect. The confidence interval is merely an indication of what confidence you want to ascribe to this. And this confidence interval is equal to 1 minus 2 eta, or, which is also equal to 1 minus beta, where beta is is the sort of represents the chance that the sample mean falls outside the value, outside the true mean, the true population mean, is this is for a two-tailed distribution. And so schematically, what that looks like is like this. We have we have a distribution, and schematically we have some value here, and some value here. I'm going to call this T asterisk, and this negative T asterisk, and the area here, this tail area, and it goes out to infinity. This tail area is equal to ATA, and 2 times ATA gives you both the tails. And the confidence interval is the area under the curve between these two values. So it's this value. And we're going to derive this distribution function. And schematically what this is saying is, given this is a probability distribution, the total area is 1. So if I wanted to be 95% confident that my sample mean represents my true mean, or I'm 95% confident that the sample mean is indicative of the true mean, then that would mean that my ATA is simply comes from this equation, right? So we could say ATA is equal to 1 minus 0.95 all over 2, which equals 0.25. And that gives you the area under this curve to the right of T asterisk. So basically this is the basic motivation. And in the follow-up videos, follow-up tutorials to this, I'm actually going to go through the tedious elaboration of deriving various of these quantities from scratch, from the statistics. Okay, so thank you for that.